Last week we started talking about complex variables and Laplace transformation. So today I'm going to continue from there. I posted these notes on the forum today, so you have this exact file, so you can refer to this file to review these topics. So we made a quick review of complex variables. We talked about complex functions, stressing out the important parts for our purposes. And then we defined Laplace transformation. So there's a defining integral. So a transformation transforms a function to something else. Okay, so originally we have a function defined in time domain. We take this function and turn it into another function which is defined in S domain. Okay, and this transformation is realized through this integral. So we take this integral over time to turn this function into a function of complex variable S. And I showed you some simple examples by using the defining integral. We, for example, computed the transformation of the unit step function. So this is our unit step function. Since we take the integral in this interval from 0 to infinity, and in this interval the unit step function is just a constant number. It's just 1. So all we have to do is to take the integral of e to power minus st. So there's just one t variable, and that is here on the exponential. So you all know how to take the integral of this. And when you insert the limits, you find out that the Laplace transform of the unit step function is 1 over s. So as a second example, we computed the transform of this function, e to power minus at. So the integral we need to take becomes this, which can be combined into one term. And then from there we get the transform of that function as 1 over s plus a. So we already start seeing the power of Laplace transformation. So the original function is this, which contains an exponential term. And when the transformation is taken, it turns into 1 over s plus a term, which is easier to deal with. Okay, so let's continue. So this is where we stopped last week. So I'd like to show you another example. But before that, we should remember this Euler's theorem. So this theorem basically gives you these two relations. Okay, so if you have the exponential of an imaginary term, e to power j theta, you can write it as a complex number including these trigonometric functions. And using these two relations, we can also represent cosine theta and sine theta in terms of these complex exponential terms. Okay, so this will be very helpful in taking the transform of the sine function, for example, which is our next example. So next, let's compute the Laplace transform of this function. So we need to take this function and put it into the defining Laplace integral. So a is a constant number. This can be directly taken out of the integral. And then for sine omega t, we use this equality. So we use this relation to represent sine omega t. So I don't really want to go through the integral step by step. It is already included here in the notes. So you can, in fact, it is very similar to the previous examples. You need to integrate these two terms, this term and then this other term, between these two limits again. And when you do everything, the complex terms or the imaginary terms somehow disappear, and you're left with this function. Okay, so the Laplace transform of this function is equal to this term. We can do this similar thing on the cosine function. Again, we use this relation that comes from the Euler's theorem. And you take the integral, and the Laplace transform of the cosine function is given by this function here. Okay, so if you look at this function, this is a rational function. If you remember what a rational function was. A rational function was defined as the ratio of two polynomial functions. Okay, so the numerator here is a polynomial. It's just a constant term. There are no s terms here, but still it is a polynomial. And the denominator is a second order polynomial, so this is by definition a rational function. And if you remember the poles we define poles as the points on the complex plane where the function is not analytic. On the complex plane, there are 2 points that make the denominator 0, right? And when denominator becomes 0, the function becomes not analytic. And these 2 points are the roots of this polynomial, and the roots of this are plus minus j omega. So if you draw them on the complex plane, these correspond to 2 points on the vertical axis, right? So if this is your real axis, this is your imaginary axis, so this is where j omega is, and then you have somewhere here the minus j omega. So these 2 points are the poles of this function. Okay? So these poles will become very important. That's why I keep showing you this. So the poles of a function gives you a lot of information about that system. Okay, so when you are talking about the dynamics of an aircraft, for example, you talk about the pole locations, and we will come to that. We will be talking about what they correspond to on the actual aircraft. Okay, and then there's this inverse Laplace transformation. I just give you the definition here. You're taking the function back to the original domain, the time domain. So this time you're taking the transform function, and from here you go back to the time domain. Again, you take an integral, and this is how you take the integral. When you're taking Laplace transformation, the integral is taken on time axis, but this time the integration is done on the complex plane. Okay, so now I would like to show you another example I just found today. Well, I suggest that you do this a lot, especially for these basic courses. You can find a lot of information on the internet. So I found these files today on the Google. I just searched for Laplace transform properties, and I was looking for the proofs as well. And then it gave me a bunch of information. I just clicked on the first one, lecture notes for Laplace transform, which is open here. It's this file. And it's just a similar file, similar to what I prepared earlier, but this I didn't go through this entire file in detail, but it is explained in a different way. It was prepared by another person, so it just shows, talks about Laplace transformation from another point of view. Okay, so you can easily find a document that works very well for you. So anyway, let me find this example. Okay, so this is an interesting example. By using the Laplace transformation definition, here we take the transform of this function. It is a function defined in 2 pieces. So let me first plot how that function looks like. Okay, so the first part says that between 0 and 2, the value of the function is equal to 1. So if we start from 0, and let me put 2 here, the function has a constant value of 1 in this interval. Okay? And when t is greater than or equal to 2, the value of the function is given by t minus 2. And it is something like this, right? Okay, so this is our function. It's a discontinuous function, and this is f of t, and we need to find the Laplace transform of this function. So you need to do this if you want to compute the response of a system to such an input function. So remember the springless damper example we studied. If we apply a force that follows this function, then to find the response, we need to take the transform of this function. Okay, so we use the defining integral. So this is how we compute the transform. And our f of t is now defined in 2 different intervals. So we can take this integral and divide it into 2 first. So the integral is to be taken from 0 to infinity, and you can take this in several steps, right? So you can divide this into two integrals as from 0 to 2, for example, e to power minus st f of t plus, then you continue the integration from 2 to infinity of the same thing. Now, since the function is defined in these two different intervals separately, what you need to do next is you insert these things into those integrals. You put 1 into the first integral and t minus 2 into the second integral, and which is already done here. So this is the first integral you need to take. This is the second integral you need to take. So the first part is really straightforward, the integral of this between these two limits. The second part is a little bit tricky, because this time you have two time terms, right? So you're taking the integral over the time axis. You have one t term here and then another t term here. So I guess you can all take this integral, and the result is this part. Okay, so this is the integral corresponding to the second one, and in the end the Laplace transform of that piecewise function is given to be equal to this function here. Okay. So we know the definition of Laplace transformation. Okay, so by applying this definition, you can transform any function into S domain. But there are certain properties which become very handy in studying system dynamics. So instead of using the integral to take the transform of every function, let's take a look at these properties first. And as you will see, by using these properties, taking Laplace transform becomes much easier. So I have some properties listed here. So let's go through these properties. The first one is this one. If you take a function and multiply it with a constant number, then the transform of this multiplication is equal to the transformation of the original function without the multiplicative term times the multiplicative term. Okay, so in other words, any constant factor can be taken out of the Laplace transform, which that comes from the defining integral. The second property is this, which is really called the linearity property. So this is the superposition principle, if you remember. If you have these two functions, in fact, you can insert a constant number here as well. So you can put a constant number here, A, and another constant number, B, and then those two constant numbers will directly appear here. So which is the superposition principle. So this is the linearity. So for example, by just using this property, you can easily take the transform of this. So if I ask you to take the transform of this function, so let me give you the function as 5 times sine 3t plus 4 times cosine 9t, then the transform of this can be taken by using the results we had from here, right? So we know that the transform of sine t is this, and then cosine function is this. So all you need to do is just combine them here, and the transform will be obtained. So you don't need to take the integral using this function. Okay, so let's see what other properties we have here. Okay, so this is a very useful one. So the differentiation property. So with the help of this property, we can turn differential equations into algebraic equations, because this property says that if you want to take the transform of the derivative of a function, it is sufficient if you know the transformation of the original function. All you need to do is you take that and then put an s in front of it, and then you get these terms due to the initial conditions. But in the end, you get rid of the derivative term, and you're left with this in the Laplace domain. Okay, so this property makes our lives very easy. So we get rid of the derivative terms. Okay, so let's see how this where this property comes from. Okay, so I would like to show you the proof of this property. So we know that the Laplace transform of a function you need to take an integral. Okay, so what you need to do is you need to put this thing into the integral. So we need to take the infinity should be here. So to take this integral, we use this equality. So we know that the derivative of so we have two time-dependent functions multiplied together. If you want to take the derivative, you first differentiate this part and then multiply with this, right? So the derivative of this first part is minus s times e to the power minus st times f of t, right? And then you need to add to this this term multiplied with the derivative of the second term, which is e to the power minus st times df over dt, right? Okay, so we need to integrate this term, but that term is equal to this term here, right? So we can write this in terms of the other two terms. In other words, we can say that this is equal to this thing minus this thing. Olmadı ki. So let's take the integral of this entire thing. Okay, So the integral of the first part is very simple. It's just this. Okay. And the second part, the integral of the second part is s is a constant number since we are taking derivative in t domain. So I can take the s term and these two minuses cancel each other and become s. S times okay. Okay, so let's take a look at this. In the limit as t goes to infinity, e to power minus st converts 0, right? So it's an exponential function, but you can write it as 1 over e to power st, and as t goes to infinity, this approaches infinity, and then this approaches 0. So you have 0 minus, and in the limit as t goes to 0, you have e to power minus s times 0 times f of 0, okay, and plus s times this integral. But if you look at this integral, that is equal to the Laplace transform of the original function f, right? So this is exactly equal to the Laplace transform integral. So this is, so let me write that here. This is equal to f of s. So in the end we get this s times the transform of f minus f0. Okay, so this is equal to 1, this part is equal to 1, e to power 0, and then f0. Okay, so this proves the first, the differentiation property. So let me just save this later. And then you can repeat this and you can obtain this relation. It is not difficult to show this part. So if you repeat this n times, then the transform of this, the nth derivative of a function becomes equal to s to power n times the transform of the original function, and then you get these terms due to the initial conditions. Okay, so you have the value of the function at the initial time and the value of the derivatives of the function at the initial time are subtracted through that. Okay. Okay, and there's an integration property which is given here, the fourth property, and this says that if you want to take the transform of the integral of a function, you have a function f of t, and you want to take the transform of the integral of that function, it is equal to the transform of the original function divided by s. Similar to the differentiation property, you can use this for repeated integrals, and if you have the nth or the transformation of a function that is integrated n times, the transform of that becomes equal to the transform of the original function divided by s to the power n. Okay, so we will see that these properties will become very useful. Okay, there's another very powerful property. This is the time shift property. Suppose that we have an original function so this is our original function. Okay, so we have this function and we call that f of t. It's just red function. And before the shifting, let's talk about this. If you want to take the transform of this function, we take the transformation in the positive time axis, right? So we integrate from 0 to positive infinity. While doing that, we in fact assume that the function has no value prior to t is equal to 0. Okay, so when taking the positive, the right side of the Laplace transformation, we assume that the value of the function is equal to 0 at negative time values. And to represent that, here's what we do. We take any function, and when you multiply that with the unit step function, you obtain a function that has 0 value at negative time values. Okay, so this is our unit step function. When you multiply this with this function, the values of the function at negative time values will automatically become 0, since you multiply that with 0, and the value of the function for positive time axis doesn't change since you multiply it with 1. Okay, so this should be 1 here, it's unit step. Okay, so anyway, so this is f of t times the unit step function. Now, let's consider what happens, or how we transform. Suppose that you know the transform of this function. Now, let's see how the transformation of the function can be taken if you shift it in time domain. So, in other words, you just take this function and you move it towards right. Okay, so instead of starting the function at t is equal to 0, we assume that the function starts at another time instant, which is t is equal to capital T. And if this is the original function, the shifted function can be mathematically represented using this term. You just shift both the original function and the unit step function with an amount of capital T. Okay, so this is the shifted function. Now let's see what the Laplace transform of this shifted function is in terms of the Laplace transform of the original function. Okay, again we use the defining integral. So this is our definition, and we assume that the transform of the original unshifted function is capital F, f of s. Now we are looking for the transformation of the shifted function. Okay, so this is the shifted function in the integral. Okay, so since the shifted function has non-zero values only in this interval, only from capital T to infinity, instead of taking the integral from 0 to infinity, we can say that it is equal to the integral from capital T to infinity, right? So this doesn't change anything, since in this region the integral, or the function, is 0. So this is what we do here. We say that this integral in the 0 to infinity interval is equal to this integral in the capital T to infinity interval. Okay? And then we do this change of variables. We call t minus capital T sigma, and then d sigma is equal to dt. And instead of t minus capital T, we insert sigma into the integral. And while doing that, the integration limits change as well. When little t is equal to capital T, sigma is equal to 0. So when we start using the sigma variable instead of the t variable, we replace the integration limits from capital T to infinity to 0 to infinity. And when replacing the t minus capital T with sigma, we get this sigma plus capital T on the exponential here. This part can be taken outside, and we are left with this. And again, this is the integral for finding the transformation of the original function f sigma times u sigma, or ft times ut, which was capital F of s. Okay? So in the end, we conclude that if we have a function f of t, u of t, for which the transformation is capital F, then the transformation of the shifted function is equal to, is given by this relation. Okay, so if you take any function and you shift it by some constant time, that constant time amount shows up as an exponential term in the transformation. So again, we can use this property in shifting any function. So if you, for example, have the sine function, what is sine of t? So imagine that this was a graph for a sine t function. So if you take this function and shift it by any amount, let's say this is the shifted one, then if the transformation of this shifted function can be obtained using this property right here. Okay. Okay, so let's give a break here and then continue after the break.